Thinking, an excerpt from these lectures on physics by Richard Feynman, which some of you may have read. So Feynman is talking about the problem of visualization, and in this particular context, he's talking about visualizing the electromagnetic field, or electromagnetic waves. And unlike quarks, which are really, really, really small, the electromagnetic field is in some sense enormous. It's supposed to pervade all space, so it's really, really big. On the other hand, it's supposed to exist at every single point, and points are really small. And so it's something that's really hard to visualize. So Feynman is talking in this lecture about a student asking him a question. Professor, please give me an approximate description of the electromagnetic waves, even though it may be slightly inaccurate. A common question students ask, can you give me a picture? And Feynman's response is, I'm sorry, I can't do that for you. I don't know how. I have no picture of this electromagnetic field that is in any sense accurate. So somebody says, can you give me a visualization? And Professor Feynman says, no, I can't give it to you. This is the problem. Why not? Why can't he give you a visualization? This reminds me of another piece of Feynman publication. So Feynman won the Nobel Prize, and for this work he did in the early 1950s. And of course, if you learn somebody won a Nobel Prize, you want to know, well, what did they win the Nobel Prize for? So people ask him, can you explain what you won the Nobel Prize for? And he had the response, if I could explain this to the average person, it wouldn't have been worth the Nobel Prize. It's a sort of fair answer. It's one of the things that physics makes physics interesting, right? If they explain to you quickly why it's something that physics or anything else is interesting, how interesting could it be? If I could explain something in 2 minutes, totally and completely, it's probably not that interesting. So, this makes Feynman seem a little condescending, right? Can you explain your electromagnetic field the way I understand it? No. Can you explain why you won a Nobel Prize? No. Makes me seem like you just sort of stole it. And sometimes you look at this impression of physicists that they just don't want to give you pictures. That's not actually the case. Feynman really actually wants to give people pictures as much as possible. He really likes to do it. So, in the case of the student asking about the electromagnetic field, he's actually trying to help the student out. Because a lot of times, when we're teaching physics, students have this problem, which is they'll be listening to somebody talk, and they'll write down equations or terms or whatever, some sort of jargon, and then they'll realize, I don't really understand what they're talking about. I don't have a good visualization. And they'll think to themselves, well, because I'm not visualizing it, I'm not understanding it properly. And they'll start to think, I just don't get this physics. I don't have a head for physics. I don't understand it in this intuitive way, the way I understand rocks and chairs and things like that. And they get anxiety about this, and they think, I can't do physics. My mind is not prepared for this. And what Feynman is trying to say in this is, don't worry that you can't visualize it. I've been studying for 25 years. I'm a master of this stuff. I can't visualize it either. No one can visualize it. It's okay if you can't visualize it. So, but that doesn't mean that we don't like visualizations. Whenever possible, we try to create visualizations. And Feynman himself was very good at doing this. In fact, I'm going to explain briefly an aspect of why he won the Nobel Prize, is that people were trying to solve equations that look something like this. So this is some really massive equation with all these letters and numbers and subscripts and superscripts, and who knows what is it. I took this from the textbook. You can't even fit it on one line of textbook. It takes 4 lines. And Feynman came to the way of visualizing this equation. So instead of all these letters and symbols, you get these pictures and squiggly lines. These are all Feynman diagrams. And in fact, in each one of these groups of symbols, A, B, and C, there's a picture that corresponds. And having these pictures really help both to visualize what the equation is saying, and also to actually solve the equation. Turns out it's much faster to calculate things using these pictures, if you know how to read them properly, than it is to working through all these letters and numbers and symbols and stuff like that. So Feynman said he really like visualization. Most physicists, I really like visualization. If I can visualize something instead of writing down an equation for it, I will do that. So the question is, why are there things that we can't visualize? Are there limits to visualization? So maybe somebody will come along and invent a better visualization for things that we can't visualize now. So 100 years ago, people didn't have a microscope which could see atoms, and now we have a microscope which kind of images atoms. And maybe we don't have a visualization now for new particles and stuff. Maybe we'll be able to come up with one in the future. So are there any limits to that? And coming with visualization would be great. When we came with visualization for DNA, then all of a sudden we understood understood a lot more about genetics. So what I want to talk about is that there are limits on visualization. There are things that we believe is impossible to ever visualize. And that's what I want to try to explain. So these visualizations, these lack of visualizations, take place in the context of quantum mechanics. So what I need to do first is say a few words about the words quantum mechanics. So probably you've heard these words before, quantum mechanics. And what people typically think of when they hear these words is, okay, this is some arcane, really abstract physical theory that applies to things that are really small. Like something to do with like atoms and electrons and something like that. That's actually not correct. It may be abstract, but as far as we know, quantum mechanics applies to everything. In fact, as far as we know, quantum mechanics are the rules of the universe. Right? It's how things operate with each other. And if we could, we would try to explain everything in terms of quantum mechanics. We believe that that might be possible in principle, but in practice we can't. The reason we can't do it in practice is because it is very mathematically complicated. Right? It takes a lot of work even to model very, very simple things. So whenever we can, we try not to use quantum mechanics to explain things, but usually underlying whatever explanation we give is quantum mechanics. So if you want to know the answer to questions like, why is the sky blue, or why does the sun shine, or why is the grass green, or why are rocks hard, the underlying explanation involves quantum mechanics. Now, I can give you an explanation, like, so why is the sky blue? So let me give you an explanation of why the sky is blue that doesn't use quantum mechanics, which is that, okay, the sun is shining, and the sunlight contains all different types of light. It contains green light, and yellow light, and blue light, and red light. And all that combines to make white light. So if you look directly at the sun, you don't do this, you'll see white light. But the light from the sun travels through the atmosphere. And the atmosphere is made up of oxygen and nitrogen. And those particular molecules happen to scatter, happen to reflect blue light preferentially. So the red light and the green light, those just go straight on through, but these molecules in the air reflect the blue light down to your eye. And so when you look at the sky, you see blue light. So the sky looks blue when the sun is out. So that explanation doesn't involve quantum mechanics. However, there's an obvious follow-up question is, why does oxygen and nitrogen, these molecules that exist in the air, why do those reflect blue light? Why not green light or red light? And if you ask them that question, they'd say, well, we have to look at quantum mechanics. So underlying almost all our explanations, if you ask the why question, the sort of why this, why that, keep drilling down, the explanation you find in quantum mechanics. It's the theory we have for how things work. I should say that the other thing is that the reason why we think it's the theory is that it's been incredibly well corroborated by experiments. Every experiment we've ever done, we can model quantum mechanically, has turned out to be directly predicted by the quantum mechanics. There's no experiment we can point to and say, that seems to violate quantum mechanics. It's incredibly predictive. It predicts all sorts of diverse things, like answering these questions. And in all different cases, we can test it all different ways, and it's passive quantum intelligence. It seems to be the theory of the way that the universe works. And so you may say,